let's continue on with section 3.4. And we talked about power sets. The power set is the set that contains all subsets of the set. And they're really big. In all the examples we've seen, the number of elements in the power set is much greater than the number of elements in the original set. So let's think of an example. There are 4 elements in the set of all suits, in a deck of cards. So all the suits here, right, there are 4 elements in this deck here. There are 4 elements, 1, 2, 3, 4. But there are 2 to the 4 elements in the power set, right? If I were to count all these out, there would be 16 here. And so we can say that 16 is much bigger than 4. So it turns out that the power sets are always larger than the original set, even if the original set is already infinite. And this is another theorem that is one of Cantor's most important achievements. Let's think about what this theorem means and its consequences. If we take an infinite set S and look at the set of all its subsets, so basically if we look at its power set, the cardinality of the set P of S, or power set S, will be greater than the cardinality of S. So how can we use this to make more and more increasingly larger infinities? Let's take the set of natural numbers and let's call it n, which we, remember the natural numbers, 1, 2, 3, 4, and it's infinite, goes on forever. What do we know about the power set of the natural numbers? The set of all the subsets. Well, let's just look at some examples. Okay, we could look at the subsets just 1, 2, 3. We could look at the subsets of 1, 2, 1, 3, 2, 3. We could look at the triples of the numbers, or the set of 4. So the triples of these numbers would be like 3, 6, 9. We could just look at the sets of 4 numbers, right? 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 5, right? We could look at each finite set of numbers. We could just say, hey, all the finite numbers. We could say the subset consisting of all the even numbers. We could say the prime numbers. We could say the Fibonacci numbers. And each of these are a subset of the natural numbers. They're all elements of the power set of the natural numbers. So Cantor's power set theorem. The power set of the natural numbers is a set that has more elements than the natural numbers themselves. So suppose we consider the power set, that we consider the set of all the subsets of the set of all the subsets. We could call this set the power set of the power set, right? The power set of the power set. And naming any element of this set would require a lot of care. What do we know about the size of the power set of that power set? We know that that power set is going to be greater than the original power set because this is within it. So now we found a third infinity, right? This guy is infinity, this is infinity, and this is infinity. We found a third infinity that's even larger. Well, can we find one that's even larger? Sure, we could find the power set of this, right? The power set of the power set of that is going to be bigger. And I could literally do this forever. So we can say that we have a way now of producing infinitely many sets, each with a larger cardinality than the last. So what Cantor's power set theorem says is that for any set, finite or infinite, the cardinality of the power set, S, is strictly greater than the cardinality of S. All right, let's prove it. Remember that cardinality is determined by one-to-one correspondence. So suppose we look at the correspondence that has elements of S on one side. So we're going to have S on one side, and we're going to have elements of the power set of S on the other side. And we're just going to match up that correspondence. Remember, that's to determine the cardinality. So we're just letting the letters A, B, C, D, and so on stand for the elements. So a pairing between the set S and its power set might look like the following. And remember that the power set are the subsets of S. Okay, so this has the element A. And we just pull it out of a barrel, right? Doesn't matter, right? And we pull out of the barrel this subset. And then the element B, and we pull out of the barrel this subset. And the element C, and we pull out this subset. So to see that this cardinality, the power set's cardinality is greater, we have to show how to construct some subset of S that doesn't exist here, just like we did in a previous section, if we can show that, hey, all of the elements of S are listed, but there's a secret missing one not listed, then we can show that it's greater. And that's exactly what we're going to try to do here. So we want to prove that between any pairing that there is a missing subset. So recall way back in that last section that we found out that we proved there were more real numbers than natural numbers by proving that there was that missing real number. And we're going to do the exact same thing here. We're going to construct an element of the power set that is not paired with any element of S. So to construct the missing subset, we're going to do the same thing that we did in dodgeball, the same thing that we did in that missing real number. We're going to consider each element of S and decide whether it's in our mystery subset or not. Okay, so looking here, let's start with when we wish to construct this, we want to make sure that it doesn't match up. So we're going to start by saying if A, we're going to start with A, should be in mystery or not. So we've got mystery here. Is some sort of subset. And remember, this is a subset of S, so it's going to have elements of S, but it's not going to be listed here. So let's start with the very first one. Do we want A in here or not? Well, let's look at what matches with this. CF. It's not in A, so we are going to put it in mystery. Okay, let's look at B. Should we put B in there? Well, when I look at the second one listed here, I do see a B. So we're not going to include B in ours. In this third one here, do I see a C? I do not see a C, so I will include a C. And the idea is I'm trying to build something that doesn't exist here. And we're going to keep asking those same questions. So now we ask ourselves, okay, so we decided that we've got, so mystery. We've got mystery. We know that there's A. We decided not to put a B. And in that third one, we decided to put a C because there was no C. And now let's look at D. Should we put D in mystery? And D, there's an empty set D. So yes, we're going to put a D because it's not in that fourth one. What about E? Well, E is, if we look here, this is the set S. And E is an element of the set S. So we do not want to put E there. What about X? X is some subset of S. Now, since they don't tell us the specific subset, let's just write it down our decision process. We'll put X in mystery if X is not in the subset corresponding to X, and we will not put X in mystery if it is the subset corresponding. And we just keep going on and on. So could mystery appear anywhere in here? And the answer is no. And it's just like when we were proving that real number. Why? Just like in dodgeball. Why? Because we designed it that way. For every move that player one makes, which you can kind of think about as these, we do the opposite. And that's how we know that the cardinality of the power set cannot equal the cardinality of the set, because there is not one-to-one correspondence. There is a missing subset. So that took a long time. Let's see if we can make it a little bit shorter. And this is it. And it actually has to do with that very last one with X, right? So with X, we kind of put a question mark here because we didn't know. If X is in a subset, then no, we're not going to put it in mystery. If X is not in a subset, then yes, we're going to put it in mystery. And that's pretty much the whole shorter proof there. For each element X of S, we will put it in if it is not in the subset corresponding to X. And we will not put X in mystery if X is in the subset. We're just going to do the opposite, just like with the X's and O's of dodgeball. And you know what? We can even make it even shorter. Which goes to show that actually something that is short doesn't mean it's better, because if I put that on the screen earlier, even now, it doesn't make sense. But what this is saying is consider a pairing from S to the power set of S. Then the particular subset consisting of all elements X that are in S will not go into the mystery set. such that X is not an element of the set corresponding to X with the given pairing and is not paired with the element of S. QED just means the proof is over. So what can we conclude after all that? We can conclude that there is indeed a set having greater cardinality than the cardinality of the set of real numbers, which we already proved was greater than the natural numbers. And this is the power set of real numbers. The set of all subsets of the real numbers is a collection even larger than the set of reals. By repeating this process successively building the power set of the previous set, we see that there are infinitely many different sizes of infinity. And we come back, we're going to continue looking at this.